Welcome, tech enthusiasts, to a topic that's quickly becoming indispensable in the world of distributed systems, building self-healing applications. Imagine a Java service that doesn't just crash and alert you, but intelligently detects its own problems, like a CPU spike or a memory leak, and then automatically fixes them, all before a human even notices. Sounds like sci-fi. Today, we're going to dive deep into exactly how you can implement the foundational concepts for such an autonomic Java service, leveraging AI principles to achieve this remarkable level of resilience. Stay tuned, because the future of robust software is self-healing, and you're about to see how to build it. In the relentless pace of modern software development, our applications are growing increasingly complex, often deployed across vast microservice architectures. While this complexity offers immense power, it also introduces a myriad of potential failure points. Think about it: high CPU utilization, creeping memory leaks, inexplicable performance bottlenecks. Traditionally, when these issues strike, monitoring tools scream, pages go off, and an army of on-call engineers scrambles to diagnose and fix the problem. This reactive approach isn't just stressful, it's slow, prone to human error, and directly translates to increased downtime and significant operational costs. We need a better way, a proactive way, to handle these inevitable runtime challenges, shifting from human intervention to automated resilience. This isn't just about catching errors, it's about giving your applications the awareness and intelligence to self-diagnose and self-heal. It's a paradigm shift from reactive firefighting to proactive, autonomous system management. Our solution, the Autonomic Java Service, demonstrates this by integrating three core pillars: continuous monitoring, AI-driven anomaly detection, albeit a simplified, rule-based one for this demo, and automated remediation. Picture it as equipping your Java service with its own nervous system and a tiny, smart brain. It continuously observes its own vital signs, identifies when something is wrong, and then autonomously triggers corrective actions to restore its health, often before an impact is even felt by users. This approach significantly enhances service reliability, reduces operational overhead, and frees up your valuable engineering talent for more innovative work, rather than constant incident response. At the heart of any self-healing system lies robust monitoring. You can't fix what you can't see. Our Autonomic Java service starts with the Service Monitor component. This isn't just a passive observer, it's an active, scheduled component that periodically collects vital runtime metrics. Think of it as the service's own internal health tracker. For our demonstration, we're simulating these metrics: CPU usage, memory consumption, and response latency. In a real-world production environment, these would be collected from actual JVM metrics, operating system statistics, or application performance monitoring (APM) tools. But the principle remains the same: gather the data, understand the current state. The Service Monitor then acts as the data pipeline, feeding this stream of health data directly into the system's analytical brain, ready for the next crucial step in our self-healing journey. Once the metrics are collected, the next crucial step is making sense of them, identifying when something is actually wrong. This is where our anomaly detector comes in, serving as the AI component of our self-healing system. For this proof of concept, we've implemented a rule-based AI. It's not a complex machine learning model trained on terabytes of data. Instead, it uses predefined thresholds. If CPU usage exceeds 90%, or memory breaches 80%, or response time spike beyond 1000 milliseconds, it flags a potential anomaly. Crucially, it doesn't just react to a single spike. We've built in a consecutive _detection threshold. This means an anomaly must persist for a certain number of checks to be confirmed, preventing false alarms from transient network jitters or momentary resource spikes. This simple yet effective logic allows our service to intelligently discern genuine issues from normal fluctuations. Once the anomaly detector confirms an issue, it's time for action. This responsibility falls to the healing service. Think of it as the central command for all remediation efforts. Its job is to orchestrate the recovery process by mapping the detected anomaly type, be it high_CPU, high_memory, or slow_response, to the correct remediation action. We've designed a clean, extensible pattern using an interface called remediation action. This means any specific healing strategy, like clearing a cache or optimizing a thread pool, can be implemented as a distinct component. When our Spring Boot application starts, the healing service automatically discovers and registers all available remediation action implementations, creating a dynamic map. So, when a high_CPU anomaly is confirmed, the healing service knows exactly which specialized fixer to call upon to mitigate the problem. Now, let's talk about those fixers, our concrete remediation action implementations. In our Autonomic Java Service demo, we have 3 distinct actions tailored for our specific anomaly types. For a high_CPU anomaly, we invoke CPU optimization action. While in our simulation this merely resets the CPU metric to a normal level, in a production system, this could trigger actions like adjusting thread pool sizes, reprioritizing tasks, or even initiating an auto-scaling event for the service instance. Similarly, memory cleanup action handles high_memory issues. A real-world scenario might involve clearing problematic caches, optimizing data structures, or in extreme cases, safely recycling the application instance. Finally, latency optimization action addresses slow_response times. Here, actual remediation could mean refreshing database connection pools, breaking circuit breakers to isolate faulty external dependencies, or re-establishing network connections. Each action is designed to simulate a targeted response, demonstrating the power of precise, automated healing. Let's walk through a real-time scenario to truly appreciate the self-healing in action. Imagine your autonomic Java service is running smoothly, minding its own business. Then, suddenly, a new feature deployment or a rogue batch job causes a CPU spike. You, as the developer or operator, trigger this by hitting the /simulate/CPU spike endpoint. Almost immediately, the service monitor will detect the elevated CPU usage during its next scheduled check. It feeds this data to the anomaly detector, which, after a couple of consecutive detections confirming the spike isn't just a fleeting glitch, classifies it as a high_CPU anomaly. The anomaly detector then notifies the healing service. The healing service, in turn, looks up the CPU optimization action and executes its remediate method. You'll observe a flurry of log messages detailing each step, the monitor collecting, the detector identifying, and the healing service performing the optimization. Within seconds, the simulated CPU usage returns to normal, all without any human intervention. This proactive, automated recovery minimizes downtime and ensures service continuity. For those who like to peer under the hood, let's briefly touch upon the structure of our Autonomic Java Service project. It's a standard Spring Boot application, making it easy to run and extend. Our pom.xml handles all the necessary dependencies, including Spring Boot Starter Web for our REST endpoints and Spring Boot Starter Actuator for basic monitoring capabilities. The main application class, Autonomic Java Service Application.java, is where we enable Spring scheduling capabilities with that enable scheduling, vital for our service monitor to periodically collect metrics. We have a service controller managing our REST endpoints for health checks and, crucially, for simulating failures. The core logic is neatly organized into packages: Monitor for data collection, AI for anomaly detection, and Healing 4 orchestration and specific